Hello, and here we are for part 2 of the explanation of how to calculate proportions in the unit normal distribution given z-scores. So I believe we already did how to find proportion of cases below a given z-score. And the question now is how to find the proportion of cases that are expected to be beyond the given z-score as, or the sample mean as represented by its z-score. We're going to be looking, so what you look for here is the adjacent tail, the above the proportional value when you have positive z-scores. These are called the tails, the narrow, small ends of the distribution. They're positive tails, and over here is the negative tail, and this is referred to as the body. And I'll show that again a little bit later. But you look in the adjacent tail. So you're talking about the proportion of values in the adjacent tail. So if you have a z-score that's at the positive range, you're looking in the right-hand tail. If you have a z-score in the negative range, you're going to be looking at the left-hand tail. It is symmetrical. So the proportions, which are only positive, proportional values only being able to be positive, are the same. So the proportion beyond sample mean in a single tail is 1, that's 100% of the distribution, minus the proportion below that value. We've already found the proportion below that value in the z-tables. So it's just all of the table, all of the possible area minus the area that is accounted for by the values you see. So we're going to go back to our two examples, one where we have a z of 1.20, one where we have a z of 0.30, and we want to know in this case what proportion of cases are beyond each sample in the tail. So because we're dealing with positive z values, that will be above 3 or above 1.20. So we know that our p below this mean of 16.5, which is represented by a z value of 1.20, is 0.8849. We found that much earlier. So in the last video. So we know that the proportion below 0.8849 from the table for the z of 1.20. This value I should probably put in z 0.20, but they're the same. So therefore, if we say 100% minus 88%, 88.49, that is below that, then 0.1151 of the unit distribution is above a mean of 16.5 or a z of 1.20, and a sample mean of 16.5 or corresponding z of 1.20, given this sample size, the population mean, and the population standard deviation, which is about 11.5% of scores are beyond that in the normal distribution. And when z equals 3, this was, oh, I'm sorry, once again, I have a mistake in here. Let me just pause and correct it. I'm sorry, I didn't have a mistake. I thought that because the means were the same, that the z-scores should be the same, but they're different because of different sample sizes. So when the sample sizes for the likelihood of a score beyond is 11.51, for a sample size of 25, 0.005. So you can look now, we've covered in part 1 this part both the proportion of values in the body, which is called the body, the major section, is usually including one tail, sometimes including one tail. I'm going to call it the body if it's one of the tails but not the other. Sometimes the body is actually more commonly, sorry, the body doesn't include either tail. That's kind of a misnomer, but I don't think it's essential. So you can also look in a tail. You can interpret those as proportions. You can also interpret them as percent. I've been switching back and forth. You can also interpret them as likelihoods. So proportions translate into probability. How likely a value will be is related to its proportion under the expectations of the normal distribution. So you can say, given the p-value of these two random samples, how likely is either mean? How closely does it resemble the population from which it was drawn? Remember, they're the same mean, but they're drawn from separate sample sizes. So you say, well, my population is 15. My sample mean is 16.5. I've only drawn 4 cases. How likely is it that I would get that? And the likelihood, you don't really do the likelihood in terms of exactly that, because remember, continuous distribution, the intervals are infinitesimally divisible, so we can't really say at. So we say above or below. And the probability you get something beyond that is about 0.1151. Now, is that likely? Is that unlikely? Think of that as being a score at the 88th percentile. It's kind of, it's a little bit unlikely, but it's not, it's B plus. It's not out of this world. You look at the other one, here you've got a lot more people, and your mean is 16.5, but with 25 people, that's at a z-score of 3. So you look and you say, well, how unlikely is that? Only a less than 1% population would have a z-score in that range, above 16.5, 16.5 when you had a sample this large. So that's quite unusual, and it's above the 99th percentile. So you see that unless you know all the ingredients, the population mean, population standard deviation, the sample mean, and the sample size, it's very difficult to compare the scores in terms of their likelihood. And this is kind of what we want to do. We want to know how likely something is, because we want to know, the question is, how likely is it under the assumption that it's a random sample from the population? And if it's really unlikely, kind of in the next class, we're going to think about, well, why did I get a sample at this percentile? Why did I get a sample that unusual? It could be random chance, but it's pretty unusual. Okay, so that's pretty much anticipating where we're going to go, but continuing to our z-scores. The other thing we might be interested in is the proportion of cases that are sample means that would be likely to be found between two different z-scores. And this is classically the body of the distribution. This is the left tail, this is the right tail. So let's say we have a distribution with a mean of 100 and a standard deviation of 25. So a score of 125 has a z-score of 1, and a score of 75 has a z-score of -1. And we don't want to find out the proportion below this value of b equals 1. We want to find the proportion in the left tail or the right tail, the total proportion that would be expected beyond either z equals -1 or z equals 1. So basically, we just take the proportion beyond either tail and multiply it by 2 because they're symmetrical. So that's actually quite easy to find the proportion beyond. You may need to remember that when you look in your textbook, get the proportion below, which is all of this area. And so to get this actual area, you have to subtract from 1. Going back to our sample 2, where we had those 25 people with a mean of 15.5 from a population with a mean of 15 and a standard deviation of 2.5, and we got that the proportion below that value, which was z of 3.998, came up with z of 3, and that has a proportion of 0.9986. So the proportion above that in the adjacent tail, the tail to the right of it, in this case, would be 1 minus that, the whole distribution minus what's accounted for below that z of 3. And so the probability, you could say, of 3 is 0.00125. If you're looking for the probability either beyond 3 or beyond -3, in either direction, either one of these tails. Now 3 is much further out, so we're going to get just a little teeny tiny bit of its tail. But nonetheless, in either tail, then you just multiply the probability of one tail times 2, and you still have a very improbable value. It's less than 1% of the cases beyond either -3 or +3. Okay, so this is our last part, which is going to be on interpreting negative z-scores. And we're going to have a new sample here. And remember a couple of things that you remember is, first thing, normal distribution is symmetrical. So, and then you have to remember we're going to remind you of your formula. So let's say that we have another randomly drawn sample. Population is the same, population of mean of 15 and standard deviation of 2.5, but in this case the mean is 14.245. So to get your z, you take that population mean, subtract it from mu, and you divide it by the standard deviation of the population divided by the square root of n. This whole term in the denominator is the error of the mean. So here you go, your values for the equation. Get a negative numerator because your obtained mean is lower than your population mean. So you're going to get a negative z-score. So the probability of getting a mean that is lower than a negative z-score, the probability in the left tail is equal to the probability of getting a mean above the positive z-score. So going back to this picture, the probability of a value being in the left tail is the same as the probability of it being in the right tail. The only confusing thing is seeing this in the tables. So when we do this equation, we get a z-score of negative 1.21, and we find the probability for z equals 1.21. That's 0.8868. Then we find the probability of z beyond 1.21, which is 1 minus 0.8868, which is 0.113. Okay, so that's the same as the formula for finding the probability in the adjacent tail. It's 1, the whole distribution, minus 0.8868, which is the values below that value. So 0.113 is, or 11.3% of the population would be expected to be above the of positive 1.21. But our question is, what is below the negative 1.21? And that is just exactly the same, because distribution is symmetrical. And the proportion in one tail above a corresponding value is going to be the same as the proportion in another tail below the corresponding value. Now, to find out what the total proportion is between both, or not between, but beyond the scores of negative or positive 1.21, you add those two probabilities. So to find the probability of a score less than the negative value or greater than the positive value, you just take that 113 and double it. Okay, so one of them just over to the left of negative z 0.113. If you want to think about how much is either this range or this range, it's 0.113 plus 0.113. Now, this has slightly interesting application, not slightly interesting, a very important application for later in the course, which is why I'm going through all these different ways of calculating probabilities in different areas of the curve. But that will be revealed. For the meantime, these are how you calculate the z-scores in terms of proportions of probabilities at different areas of the normal distribution. And I think that's pretty much it. That is just kind of the finale of that group. And so we will end here.